Okay, we're going to start off this discussion about PVnRT, PV equals nRT, also known as the ideal gas law, and gas stoichiometry, by taking a little bit of a visit back to the combined gas law. Sorry, I want to turn the volume up. All right, so just to renew, just to refresh ourselves, this is the combined gas law. P1, pressure of a gas at a certain volume at a certain temperature in Kelvin, is going to be equal to the same sample of gas at a different pressure, different volume, and a different temperature. And we can set up a relationship to solve for any one of these variables, knowing the other five. Right? So if we look at that combined gas law, what we've seen is that the volume of a gas is proportional to the inverse of the pressure. That was Boyle's law. We've seen the volume of a gas is proportional to the temperature, direct relationship. That's known as Charles' law. And that the volume of a gas is directly proportional to N, N being the number of moles of that gas. And that's known as Avogadro's law. If we combine these and those previous relationships, we can say that the volume is proportional to the number of moles of the gas at a certain temperature in Kelvin over the pressure of that gas. Mathematically, we can, instead of setting up a proportion, set up a constant, and then we can set up an equality. So the volume of a gas is equal to some constant times the number of moles of that gas, temperature in Kelvin, divided by the pressure. Oops. Rearranging this equation, we get PV is equal to nRT. This R is known as the ideal gas constant. And an ideal gas is one that pretty much follows the kinetic molecular theory. Okay, kinetic molecular theory. All right, how are we going to use PV equals nRT? Well, let's calculate a value for R first, that universal gas constant. I call it the ideal gas constant. All right, we can calculate this by using the molar volume of a gas at STP. Calculate STP, we use 273 Kelvin, 1 atmosphere, 1 mole of a gas, and the molar volume is 22.4 liters. We're going to rearrange PVnRT, and let's do that real quick. If I end up with PV is equal to nRT, I can get R by itself by dividing N over T. If I do it to this side, I have to do it to this side. The N cancels, T cancels, R, universal gas constant, is equal to PV over NT, which is what we have right there. Plugging in the pressure, STP is 1 atmosphere. Volume of 1 mole of gas at STP is 22.4. 1 mole, 273 Kelvin is the standard temperature. Divide all that, look at the units. 0.0821 liters times atmospheres over mole Kelvin. Cool. So, how much do we know? What is the value of R when we substitute in a pressure of 760 millimeters mercury? Take a minute, see if you can do it. Did you pause it really? All right. Set up the same way. Instead of 1 atmosphere, you use 760 millimeters mercury. So we come up with a second value for the universal constant, just with different units. 62.4 liters millimeters mercury over mole Kelvin. If I'm honest, I don't remember this one. I always use 0.0821 liters atmospheres over moles Kelvin. What I do is I just convert everything to liters, to atmospheres, to moles, and to Kelvin, so that I can use the R 0.0821. All right, so let's work this a problem in practice. I have dinitrogen oxide, laughing gas, is used as dentist as an anesthetic. If a 20-liter tank, that must be the volume because it says liters, so my volume is 20.0 liters, of laughing gas contains 2.86 moles of dinitrogen oxide. That's N, N is 2.86 moles of N2O at 23 degrees Celsius. Okay, well, that 23 degrees temperature, 23 degrees Celsius, but I remember I can't use Celsius, so I have to make that into Kelvin by adding 273. Let me write that step out. Plus 273 gives me the temperature in Kelvin, which is 296. And it's asking me what the pressure is. Okay, well, I've got a volume, I've got a number of moles, I've got a temperature, and it's asking me for pressure. Well, seems to me I have most of the variables needed to use PV equals nRT. I'm looking for P, so I want to isolate that in the equation. So I divide both sides by the volume. This volume cancels out. I get P, pressure, is equal to the number of moles times R times T over the volume. Do I know the number of moles? Yes, I do. 2.86 moles N2O. R is 0.08, that's a 0, 21 liters, atmospheres, moles, Kelvin, times my T, that's 296 Kelvin, over my volume, which is 20.0 liters. Now the first thing I want to do is I want to make sure that I set this up right. So I'm going to look at how things cancel. Moles in the numerator, moles in the denominator, those cancel. Liters and liters. Atmospheres don't cancel. Kelvins cancel though. Atmospheres don't cancel, so my answer must have atmospheres. Hey, I was looking for pressure. That works out well. So on my calculator, I'm going to take 2.86 times 0.0821 times 296, and I'm going to divide that by 20. I get an answer of 3.475 atmospheres. Look back, sig figs, that changes to 3. That's 3 and 3, so I should report my answer to 3 sig figs. 3.48 atmospheres is my pressure. Important things to note. Important to show me what equation it is you're using. Okay? If you need to start at the PV equals nRT, please do so. Solve the equation in terms of the variable you're looking for. Isolate that term, then plug in the numbers and the units. Then solve for the variable. All right, how does this relate to stoichiometry? Here it's asking me what volume of gas is needed to completely react with 15 grams of aluminum at STP. All right, so I've got, here's my given, 15 grams of aluminum. I want to know the volume of oxygen. I have STP, so my pressure is 1 atmosphere. My temperature in Kelvin is 273 Kelvin. Well, that aluminum is definitely not a gas. Oh, it's telling me oxygen and aluminum react together. Oh, all right, so I've got aluminum, which is a solid, plus oxygen gas. Well, what would they do? Well, they're elements, so they must make a compound. Well, the compound's probably made out of aluminum and oxygen. Oh, it's probably aluminum oxide. Metal, non-metal, that's an ionic. Oh, okay, so aluminum oxide. It's an ionic compound, so chances are it's solid. Al2O3, because the aluminum is a +3, oxygen -2. For it to be neutral overall, I need 2 aluminums and 3 oxygens. Okay, that's cool. Oh, it's not balanced. It's not. I got 3 oxygens over here. I have 2 over here. Common multiplier is 6, so I guess I need 3 here. And I need 2 here. That makes 6 oxygens and 6, and then that's 4 aluminums. So now I got a balanced chemical equation. So now I can take these grams of aluminum, convert them to moles, use the mole ratio with this balanced chemical equation to get to moles of oxygen. Once I get to moles of oxygen, I have a pressure and a temperature, and the moles, ooh, PVnRT. Hey, that's kind of cool. Let's do that then. So, changing colors just so we can follow along. So I have 15.0 grams aluminum times grams of aluminum in 1 mole. This is 26.98 grams, and that's moles of aluminum. For every 4 moles of aluminum, that's from this balanced chemical equation, I get 3 moles, or actually I need 3 moles of oxygen to react with it. That's going to give me the moles of O2. Then I can use PV is equal to nRT. I want to know the volume needed, so I have nRT over P. Oh, so let's find out these moles first. So I've got 15 divided by 26.98 times 3 divided by 4. This gives me 0.411698. I carry more sig figs that I'm going to have to round to at the end. I think I'm going to round to about 3 because that's my given. Alright, so then down here for the volume, I need N. That's the number of moles of oxygen. Times R, 0.0821 liter atmospheres, mole Kelvin, times T. Don't like to do this, but I ran out of room, over the pressure 1 atmosphere. This temperature should be there, but I ran out of room. So moles will cancel, kelvins will cancel, atmospheres will cancel. That leaves me liters. Hey, I'm looking for a volume. That works out. All right, so I take my moles of O2 times 0.0821 times 273 and then divided by 1. So I get a volume of 9.346 liters of O2, but I need 3 sig figs, so I'll make it 3.5 liters of O2. Right? So this PVnRT just gives me a way to get to pressure, temperature, moles, or volume given the other 3 and using that ideal gas constant.